Hi, and welcome to the Machine Learning Final Project by Eric and Robin. In this project, we'd like to explore CNN to classify images. So we aim to build two classifiers, gender classifier and age classifier, that can respectively distinguish a person's gender and age based on his or her image. So the gender classifier should be able to tell whether or not a person is male or female, and the age classifier should be able to tell the approximate age range for a person in the image, such as whether or not a person is child, teenage, youth, wrinkle, or elder, as shown on the left-hand side. And numbers below are corresponding predicted age range for that person. Dataset we use is UDK face dataset. It consists of over 20K face images with annotation of age, gender, etc. And the images covers large variation in pose, facial expression, and resolution, etc., etc. So on the left-hand side, it is a sample subset of this UDK face dataset. And to pre-process our data, firstly, we randomly select images to fulfill our training set and validation set. For gender classification problem, we randomly select 8,800 images from UDK face dataset with equal distribution of male and female. For instance, on the left-hand side, in the training set folder, so the number of female images are actually exactly the same as the number of the male images. And it is also the same for validation set. And similarly, for age classification problem, we also randomly select over 8,000 images from the dataset with equal distribution of 5 types of ages, same as the male and female scenario. And because of that, we don't have an unbalanced data problem here. And afterwards, we reshape our data into the same size of 224 and 224 by 3, so that all of the original images now have the same size. And afterwards, we flip the image horizontally, or simply let the image remain a status quo with equal probability. And to do that, we call random horizontal flip function within a transforms package. And afterwards, we convert the incumbent image data into tensor type. And then finally, we normalize all of our images with corresponding mean and standard deviation using the transforms.normalized function for all of these RGB channels. And that's why on the left-hand side, we have two 3x1 vectors. And just to visualize the transformation effect, so before the transformation effect on the left-hand side, we have 4 different images with different size. And then after the transformation, we can see that all of these 4 images are compressed into the same size of 224 by 224 by 3. And then afterwards, additionally, we can also see that some of the images are horizontally flipped. For instance, the fourth male here that I've circled with my mouth, his image is horizontally flipped, as we can see on the right-hand side. So that was basically the data preprocessing technique.
In this part, I'm going to introduce the model we used for our tasks. We choose to use transfer learning in our model. Due to the large dimensions of each image and the confined computational power of CPU, it's difficult to build a model from scratch and train it. Therefore, we decided to use pre-trained models to build our classifiers. Specifically, we can import pre-trained neural networks such as VGG16, ResNet, and base our training on this imported network. To start, we need to choose appropriate pre-trained model for our task. We tried out different types of neural networks, and we finally determined to use ResNet 18 to be the model we are going to use. There are 2 reasons for us to choose ResNet 18. First, it performs well for our task. As we can see in the graphs on the left, it provides a performance comparison between AlexNet and ResNet 18 on gender classification task. The accuracy of ResNet 18 is about 0.94 and the accuracy of AlexNet is about 0.64. Second, ResNet 18 has rich feature representation ability, which we'll discuss next. Here we give a brief introduction to ResNet 18. ResNet 18 is a convolutional neural network which is trained on more than 1 million images from the image dataset. The network is 18 layers deep and it can classify images into 1,000 object categories, such as keyboard, mouse, pencil, and many animals. Therefore, the network has learned rich feature representations for a wide range of images. To build our own models based on ResNet 18, we first remove the original softmax layer, then we replace it with a new softmax layer for both classifiers, and then train our model based on these two tuned models. In the new models, X is input value, which is a 224 by 224 by 3 image. The output value Y for gender classifier is the 2 by 1 vector, indicating whether the person in image is male or female. The output value Y for age classifier is the 5 by 1 vector, indicating age range for the person in image. There are two approaches we can use for transfer learning. One is fine-tuning and the other is freezing layers. We choose to do fine-tuning on the CompNet instead of freezing layers because training on a relatively large training set, fine-tuning has a better performance compared to freezing all the layers. The graphs on the left shows the performance using fine-tuning and freezing layers. The green and red line corresponds to fine-tuning and the blue and orange lines correspond to freezing layers. It shows that fine-tuning achieves higher prediction accuracy both on training sets and validation sets. Then we need to choose suitable optimizer for our model. We used a small image set and tried out many combinations of optimization algorithms. After comparison, we select SGD with momentum to be our optimization algorithms. The reason is that SGD is faster and generally yields performance better when compared with other algorithms like ADAM, IMS prop, and extra. For example, the graphs on the left shows performance comparison between SGD algorithm with momentum and ADAM algorithm. Using SGD, we achieve higher training and validation accuracy than ADAM. We also need to choose suitable hyperparameters for our model. We used the same small image set as one we used when choosing optimizer. After trying out many different combinations, we found the following hyperparameters yield very good performance. We choose the learning rate to be 0.001, the momentum to be 0.9, and the weight decay to be 0.1.
So after the training, let's take a look at the result. Both classifiers' performance graph are shown on the left-hand side. So as we can see that after training, gender classifier has an over 90% accuracy rate, whereas the age range classifier has around 75% accuracy rate on validation set. And since training and validation data are equally distributed for each class for both classifiers, we don't really face an unbalanced data problem here, and therefore we didn't really need to use ratios such as true positive rate or false positive rate to measure our resulting performances. And in summary, with transfer learning technique combined with carefully selected optimization algorithm, hyperparameters, and a regularization technique, we're actually able to gradually improve both models' accuracy rate and achieve a relatively speaking high and satisfying result. If we have more time, there are three potential future work that we can do. Firstly, we'd like to increase training data amount so that performance could be improved. And secondly, we'd like to train on an even larger neural network such as ResNet 50 or VGG90 and see if the performance could be improved. And finally, we'd like to borrow GPU computational power from Google Cloud to improve the computational power. And that's it for our presentation. Thank you. Here are the sources cited.